Good morning, everyone. Welcome to a special lecture by the Math Club. Today we have with us Professor Subhojoy Gupta. He works in Teichmuller theory and he has done his PhD from Yale University in 2012 under IISc. He is currently a professor at the Indian Institute of Science, Bangalore, and today we'll be talking on tilings and surfaces. Over to you, sir.
Okay, all right. Yeah. Thanks. Thank you all for coming on a Saturday morning. This fancy auditorium. I mean, the last time I gave a math club talk, it was several years ago. I think maybe 7-8 years ago, and maybe not the students are all different, I suppose. That was in a smaller room. But anyway, I'm glad to be here. Thanks for the invitation. You can all hear me, and I've got a little bit of a bad throat, so in case folks want to come in front, you can feel free to. Okay, so last time I was here, I talked about something completely different, but so this time, so I'll talk about tilings on surfaces. Okay, and it'll be a sort of a relaxed elementary talk for all of you. Okay, so feel free to ask questions and stop me. It's nothing too complicated, but I like it because it is connected with a lot of different complicated things and different subjects in mathematics, and hopefully we'll see some of these connections in this talk, ranging from groups and combinatorics and geometry topology, and as well as theory of computation and so on. So tilings is related to many of these things, and so I thought it would be a nice thing to expose it to all of you in this math club. But it is also a very vast topic. Okay, so there are many things one can study in tilings. It's an old topic of study also. So I'll concentrate today on what are called regular tilings and semi-regular tilings, and of course only on surfaces, and these will be the surfaces of the Euclidean plane, the hyperbolic plane, and some other sort of compact, closed, oriented surfaces that I'll tell you about. Okay, so I'm going to limit ourselves to these in this talk. So let me start with regular tilings in the Euclidean plane, and these are all around us, right? So the first example is something we see all the time, right? So it's on the ground right now, and so on, and so this one is it's a portion of one of the friezes in the Taj Mahal. This is something in Pompeii. So these have been, they're present throughout and ubiquitous in everyday life, in fact. And these tuples here, they denote, so here there are 4 squares around each vertex, right, each corner, right? And so that's what this denotes. Okay, so this 4 stands for the number of sides of each of these polygons that are the tiles, right? So this is like 4 to the power 4 is a sort of a shorthand for 4, 4, 4, 4. This is 6 cubed because there are 3 hexagons around each vertex, right? And this is the equilateral triangle tiling, and 3 to the 6, right? So these are some examples of tilings but more formally, right, mathematically, so the way you can define a tiling of a surface, it's a partition into these tiles, into these closed regions. And so for me, today we'll only talk about polygons. Okay, so these tilings would be like polygonal regions bounded by straight line segments, straight lines in whatever geometry we'll be looking at. So right now, looking at Euclidean geometry. And these regions, what's a tiling? Well, it's a covering of this whole surface where the interiors are disjoint. That's the first thing. So they don't overlap, right? Tiles don't overlap. And the second one is also sometimes called edge to edge. So if two tiles are adjacent, they have to agree on either a vertex or a one side, right? So then it's not more than that. Okay, so that's the condition. So for example, this particular tiling, which is also commonly we see quite often, but so it's not a tiling by rectangles because they don't meet. If you think of these tiles as rectangles, they don't meet along a common edge, right? So these edges overlap. So this second condition disallows that. But if you think of them as hexagons, right, where sort of you have 6 vertices, right? So then they are, and then so it's actually a tiling by hexagons, not regular hexagons, of course, but these are tiling by hexagons. Okay, but we'll in this talk we'll only talk about tilings by regular polygons. And in fact, so here's a definition. So first of all, a size of a polygon is the number of sides that it has. And we'll be talking about tiles which all have the same size and are regular polygons. Okay, so we're talking about the Euclidean plane, then it's the Euclidean polygons. And it's regular if each vertex has the same number of tiles around them. Okay, so that's going to be another one of our conditions in being a regular tiling. And in fact, you can sort of add in one more, which it turns out is redundant for Euclidean tilings, but we'll keep it on because it might be useful later. So I've written it informally here, but it has to do with the automorphism group of the tiling. Okay, but so what it roughly informally says is that the tiling looks the same at every vertex, right? So if you stand here and look at the tiling, it's exactly the same as you stand here and look at the tiling and so on, right? So this is another feature of what a regular tiling should be. Okay, so it's easy enough for you to figure out that there are exactly 3 regular tilings of the Euclidean plane, right? And then there are the 3 ones which we started off with, that you see in everyday life, right? So the tiling by the square, by the equilateral triangle, and the hexagon, right? And it's easy enough to see why, because you can calculate the interior angle of a regular polygon and see that you can't have these fit around a vertex to add up to 2 pi unless it's one of these 3, right? And once you have one of these 3, it's also easy to build a tiling. So let me just tell you very quickly. So you can build one. If you start with one of these 3 regular polygons, you can reflect along its sides, right? And you sort of repeated reflection fills out more and more of the plane, and ultimately you get all of it, right? So I guess I lost patience here drawing these things and adding them. So, but eventually you get the idea, right? So and it's the same for each of these regular ones, right? So and this is okay. So it's good to keep in mind this process of reflection, because we're going to come back to it later as well. Okay, and so one of the things happens is that these reflections are isometries of the plane, right? So they preserve the distances and so on, and it's and this group of reflections is a group of isometries of the plane, and that's going to take every vertex to any other vertex. There's a sequence of these reflections. This is the third condition of regular tilings that I was mentioning, right? So there's every vertex looks the same. So there's an isometry of the whole tiling, preserving the tiling that will take any vertex to any other vertex. In fact, not just any vertex and edge to any vertex and edge. So anyway, so reflection group is a kind of a big group, reflections on the sides of this polygon that acts on this plane, preserving the tiling, and acts transitively on all the vertices, and more than that, actually transitively on vertices and edges and things like that, right? So that's the sort of the group behind this all, and we'll see versions of it in other geometries. So let me go to other geometry, the hyperbolic plane, right, which some of you might already be familiar with, but let me nevertheless give a quick overview of the geometry of the hyperbolic plane. There's this non-Euclidean geometry, and we're going to look at only this one of these models of the hyperbolic plane, called the Poincaré disk model, where you look at the interior of a unit disk, the plane, and give it this Riemannian metric, okay? And you need not understand exactly what this means in case you don't know what a Riemannian metric is, but because I'm going to describe some features which is going to be important for us. So for the first thing is that the boundary circle that I've drawn here, the disk is sort of really what we're interested in is the interior of the disk. Okay, it's the open unit disk, but the boundary of that open unit disk, the boundary circle, is actually infinitely far away in this metric. Okay, and you can kind of guess that it would be because if you look at this expression written in polar coordinates, the denominator as r tends to 1, this factor there blows up, right? And so the distances kind of go off to infinity, and one can check that in fact, so if you're inside the space and you're sort of moving at constant speed in this metric, in constant speed, you will never reach the boundary, right? So it's sort of an infinite distance. Okay, so that's one feature. The other feature is that geodesics, which are the distance minimizing paths, right? So the analog of straight lines in the Euclidean plane. So the geodesics in this hyperbolic plane are semicircular arcs perpendicular to the boundary. Okay, so this includes the diameter. Okay, that's an example, but you have these other semicircular arcs. So any semicircular arc that's perpendicular to the boundary is actually a distance minimizing arc. Okay, so that's another feature of this metric, and a curious feature which is different from Euclidean geometry is that the sum of the three interior angles of a hyperbolic triangle is strictly less than pi. Right? So, of course, in Euclidean plane it's equal to pi. Here it's not, and right, and so this is sort of I've just drawn various triangles. So you can think of these as all equilateral triangles, in fact. And as you make these sides larger and larger, you kind of limit to this triangle, which has its vertices off at that boundary at infinity. Okay, so the vertices have actually disappeared. This is something that is called an ideal triangle. And these ideal triangles, the sides are these semicircles which meet at 90 degrees here. So the angle, of the interior angle of this ideal triangle is actually 0. Okay, so angles, as you make the side lengths of this equilateral triangle larger and larger, these interior angles actually go off to 0. And as you make it smaller and smaller, it's actually going to look more and more like a Euclidean equilateral triangle, because if you look at this expression and put in r 0, right? So then, or r is very close to 0. This it almost looks like this is the Euclidean metric. If you know this expression is something that's you probably have seen with computing double integrals and so on. This is a constant times this. So for r is 0 or close to 0, and so this is approximately Euclidean as when you go very small. So there the angles are like the angles of a equilateral triangle on the Euclidean plane, right, which is 60 degrees, and so but it can be anything between 60 and 0, right? So so this is what this picture is about, and there is one. In fact, yeah. So there's also one such hyperbolic triangle for every triple of interior angles that sum up to less than pi. Okay, this is also something you can just play around with whatever I've told you and sort of come up with some semicircles, right? So these are triangles bounded by these geodesics, right? So geodesic sides. So you can you build a triangle with these prescribed interior angles. So you already see there's a lot more flexibility here now, right? So angles can be, even for regular polygons, angles can be different kinds of angles, and so there are many more regular tilings. So here's a fact about polygons. Let's now sort of go to polygons instead of triangles. So this is the same picture really that we had for triangles, where so this time taking our regular octagon, right, and making the side lengths vary. And so when it gets very large, then we have this sort of ideal octagon with the interior angle 0, and when you're very small, then your ideal a regular Euclidean polygon or octagon with interior angles whatever it is for a regular Euclidean octagon, right? So in fact, for a regular Euclidean k-gon, this is the interior angle which we had in a previous slide as well, right? So so for an octagon, the k is 8, so it's 3 pi by 4, right? So that's the interior angle. So anything between 0 and 3 pi by 4 is actually achieved by a regular octagon. Okay, so as you vary the side lengths, these interior angles vary continuously as you sort of change the sides. And so in between, for example, there's something which has 90 degrees, right? So there's a right-angled regular hyperbolic octagon in the hyperbolic plane. Okay, and once you have something like this, for example, this right-angled regular octagon, you can reflect on the sides just like we did before and build a tiling. Okay, so if it's right angle, there will be exactly 4 that fit in around each vertex. So this is one of these 8, 4 tilings, right? 8 to the 4 means 8, 8, 8, 8 tilings, right? So this, so 8 octagons around, 4 octagons around each vertex, right? So, and you can do it for, so for any k-gon, right? So you find the appropriate angle and you find regular tilings. You can vary this 4 here as well, because there's a lot of flexibility in tilings, right? So here's another picture which we'll come back to again. By the way, I should mention here that some of these figures is not drawn by me, but taken from the internet. I've taken that liberty. This is, I think, from the internet. Right, so this is a 3-7 tiling where these equilateral triangles, but there are 7 around each vertex. All right, so so you need an interior angle of 2 pi by 7, right? So around here, and so that yeah.
Do all the triangles here have the same side lengths in that distance?
Yes, yes, right. That's a good point which I forgot to mention. The fact that these distance factor blows up as you go to the boundary, so means that things which look the same size looks maybe different when we see it as it is, right? The Euclidean metric. What we are used to is the Euclidean metric on the disk, right? So in fact, there's an octagon here, right? There's an octagon here, of course, in the center. When you reflect it, you get an octagon of the same size. These reflections, I should mention, across geodesics is again an isometry of the hyperbolic plane. Okay, it preserves distances. And so when you reflect along a geodesic, you get this octagon here, which is actually of the same size as this. It looks smaller because the way distances are measured, blows up as you go towards the boundary. So as you go towards the boundary, these octagons are getting smaller and smaller, but they look smaller and smaller, but they're actually of the same size in the hyperbolic metric. Okay. Yeah, thanks for the question. Okay, so same here, right? So all of these triangles are the same equilateral triangle, isometric, but as you go towards the boundary, they look small, but they are actually the same size in the hyperbolic metric. Right, so once again you can sort of you build one of these by taking a triangle and reflecting on the sides. I guess this one, right, that's I should have mentioned here that these two are actually dual to each other, right? So you can imagine that, so here there's 7 triangles around every vertex, right? So maybe you connect the barycenters of sort of the centroids of each of these triangles by geodesics, and you'll get regular heptagons, right? 7 gons, and then you'll get a dual 7 to the 3 tiling. Okay, so it's not hard to imagine that. But you can also start with a heptagon if you like and reflect. So there are many ways to come up with these tilings. And in fact, here's a group that is called a triangle group that's behind all this, these regular tiling pictures, which is you start with a hyperbolic triangle with interior angles pi by p, pi by q, pi by r. Of course, you need to, so if it's a hyperbolic triangle, it must add up to something less than pi. Right, so here I'm thinking of p, q, and r as integers, right? And if you take some such thing and then you start reflecting, doing this reflection process that we mentioned earlier, so you end up generating a tiling. Okay, so you have to. Okay, so it might. Right, so here I've started with something. Right, so you can start with 2, 3D. Triangle. The 2, 3D just means the angles are pi by 2, pi by 3, pi by d. Okay, so PQR triangle group is this one, pi by p, pi by q, pi by r. And so when you start with this and you keep reflecting, this is the sort of the picture, the sort of the fundamental triangle that you start off with. And then you sort of fill out, and then you can group some of these tiles into these triangles, and you can get to 3 to the d tiling. Okay, so here d is equal to 7 here. But this process you can do for any d bigger than or equal to 7, and you get, this is another way of generating these 3 to the d tilings. Okay, and this triangle group is it's a subgroup. It's a discrete subgroup of the isometries of the hyperbolic plane. Okay, so as I said, reflections are isometries. Any reflection on this geodesic is isometries. So this triangle group is a group generated by these reflections. So it's a subgroup of isometry groups. And maybe I should say a little bit more about this isometry group. So reflections, they reverse orientation, but you can compose two of them to create an orientation preserving isometry, and this is often kind of useful. And sort of, I've just taken these three pictures, I think, from a book which I'll advertise at the end of the talk. But so these are the three kinds of orientation preserving isometries that might arise this way. So here's one type, which is a rotation. So just like in the Euclidean plane, if you reflect about two lines which intersect, you get a rotation, right? And the same thing happens here in the hyperbolic plane. So if you reflect around two such geodesic lines with angle alpha in between them, then you get a rotation by angle 2 alpha, right? And if you have reflect along lines which don't intersect, right, which are disjoint, then you get a translation, right, just like in the Euclidean plane. And so there are hyperbolic translations. These are called elliptic elements, these rotations in hyperbolic plane. And there are also something called parabolic elements, where you look at reflections or translations, if you like, composition of two reflections about geodesic lines that have a common point in the boundary at infinity. Okay, so these are called parabolics. So elliptic, hyperbolic, and parabolic, three kinds of orientation preserving isometries, and maybe I'll mention a little bit more about these later on. And amongst them, so this is sort of what all orientation preserving isometries look like. And notice that the only kind of isometry that has a fixed point in the hyperbolic plane are these ones, right? These elliptic ones, right? So where the center of rotation is the fixed point. Okay, so right. So I guess in the Euclidean case we don't quite have this type, but we do have translations and rotations, and right. So those are isometries and the compositions of them, right? So the orientation preserving ones. So if you want all of them, you include reflections also, right? So reflections along lines. Okay, so these isometries would come in useful, as we'll see, to get regular tilings on other surfaces. Okay, so by surfaces I mean these, right? So these are, I'm going to only look at closed orientable surfaces. All right, so they're classified by the genus as resultant topology, and so genus 0, 1, 2, and so on. All right, so we'll start with genus 0, right? That's the sphere. Okay, and so here you can talk of the spherical geometry, which is also non-Euclidean, right, on the sphere. And you're quite familiar with the fact that geodesics are arcs of great circles, so this is what a triangle might look like, right? And you do have triangles with angle some more than pi, right? So that's the feature of this non-Euclidean. And so here are these regular tilings of the sphere. So maybe I'll show you the tilings on the sphere itself. We can get them by projecting, these polyhedra, the shadow of these on the sphere, so that you do get these polygonal regions, polygonal tiles in the sphere, and so on. So these are, you might already know, these are the only ones which have all regular polygons of the same size, with the same number at every vertex, right? And in fact, it also has, this every vertex looks the same, right? So this you can say, automorphism group is big enough, right? So these are the familiar solids, the Platonic solids, And these are the only regular tilings of the sphere. Okay, so there are exactly 5 of them. And why 5? Well, one way of figuring out that there are exactly 5 is a simple enough application of Euler's formula, which you might have already come across, right? This is sort of where the beginning of topology in some sense. And here's a quick sort of recap of how that would go, that argument would go. So once you know that V minus E plus F equals 2, right? And if you know that's a regular tiling, so there are Q p-gons around each vertex, right? Then you can count the number of edges in 2 ways, right? So you want, one is in every vertex you have, well, exactly Q edges, right? Emanating from every vertex, right? And so you can count it that way, or you can sort of count the number of faces, the Q faces. So every face has P edges bordering them because they are p-gons, right? So P times F is twice of E because each edge is counted twice, right? So you have 2 adjacent faces counted, and similarly the vertices would count each edge twice because every edge will have 2 endpoints, right? So 2 vertices in it. So you get this, and then when you plug that into the Euler's formula, you will see that the number of edges has to be this, okay? And this thing only has finitely many solutions for integers P and Q, right? You want E to be an integer, right? So number of edges. And so the only possibilities are in fact the ones corresponding to the 5 Platonic solids, okay? Right. Okay, so this is sort of a quick reason why 5. Of course, you have to show that the Platonic solids exist, but that's a different thing. You already know it in some sense. So that was the sphere, okay? So the 5 regular times. What about a torus? Well, on a torus, these regular tilings that we saw on the plane, you can use that to build tilings of the torus, because you can take a quotient of the regular tilings of the plane, the quotient by isometries, a discrete group of isometries acting on the plane. So here's an example. So here's the regular tiling on the plane with squares. And you can imagine that you have a discrete group generated by 2 translations, right? So you kind of, you have translation by some number of steps on the right and some number of steps from top to bottom. And you kind of, so you have that group acting on the plane, and the quotient is, you identify points in the same orbit, right? To 1 point. That's the quotient, right? So here the quotient would be again a torus, right? So this is something that's familiar to you, because if you take a rectangle, right, so what happens when you identify points which are identified by these translations? Well, any point in each of these rectangles is identified at some point here, right? So it's enough to take this one rectangle, because that's the fundamental domain of the action, and the 2 sides are related by a translation. So this point is identified with that, and there's also a translation from top to bottom. So all these rectangles in this vertical column also kind of get identified with 1, and in fact this bottom edge is identified with the top edge. So you have a rectangle with sides, opposite sides identified, that's a torus, right? So, and this, we have chosen these translations to preserve this tiling, and so that descends to a tiling of the torus, right? And you can do that with, the hexagonal tiling as well. So there are different ways you can do that now, by the way, right? Because you can choose this translation step to be, whatever you want, right? So some integer multiple of this, whatever the side length of the square is. So you get lots of possible, regular tilings on tori. Yes?
Once you fix the lengths of the two curves that you generally find by Euclid,
Mm-hmm.
then you get some restriction on the side lengths of these tilings.
Yes, that's right. Yeah, so you want it to be like an integer multiple of the side lengths of here, right? So you want the translations that you choose to kind of really preserve the tiling, right? So that's right. Yeah. So you get a torus. Yeah. Okay. So this actually relates to a different question, which those of you might know, that there is actually not. I mean, if you think of tori, there's a moduli space of tori, right? So there are different tori conformally, right? Even if you think of it in terms of the Euclidean metric, right? So you can have a very long and skinny rectangle, thin rectangle, and when you glue it, it will be a thin tube, right? Whereas you can take a fatter, something which is square, let's say, and that will be a more sort of a less skinny rectangle and less skinny torus, and so those are different in terms of the Euclidean geometry that it inherits, right? So by the way, I should mention that this tori, you can talk of Euclidean distances here as well, because you're quotienting the Euclidean plane by isometries. These translations are isometries, so you can talk of the Euclidean distance sort of descends down below. And so there's a moduli space. So you can, right? So you can ask, for example, that okay, so what are the so what points are in the moduli space are tiled by, let's say, squares, or tiled by, have regular tilings by squares or hexagons or triangles. So you can ask those questions, which are in this setting, and for the torus it would be easy enough, I would imagine, but higher genus, as we'll get to, these things might get. You can try to pose interesting versions of these questions. Okay, so here's the one example of higher surface of higher genus. So the way that you get a surface of higher genus is one way. So here's a picture for genus 2, right? So you can take an hyperbolic octagon in the hyperbolic plane, and this time actually you want an interior angle of angle pi by 4. Okay, so this is also possible, right? It's between 3 pi by 4 and 0, right? So pi by 4 interior angle is possible. So you take an interior angle pi by 4 and you glue sides this way. So the side C goes to C, D goes to D, and so on. Then it turns out you get a genus 2 surface. Okay, so this is something you can check. You can try to imagine what this gluing looks like. The torus is an easy thing, right? So for you to picture that you do get a torus, this is slightly more difficult, but you do get something where, and these edges glue up to give you these curves, and because, and all of these vertices, by the way, get identified to this point, single point. And because you had pi by 4, the interior angle, so they fit together nicely, and there are 8 of them, so they fit together to give you a 2 pi angle around that vertex, right? So that's it's a nice enough surface. It's a hyperbolic surface. Okay, so it's a you get it from the hyperbolic plane. So these. So I should have mentioned here that these gluings, these identifications that I'm doing are by hyperbolic translations, which are isometries, right? So we saw that there are these translations, analog of Euclidean translations in hyperbolic planes. So you can use those to identify, and you do get a hyperbolic metric here. Okay, and this is how you get a surface of higher genus. And if you So now this is again the picture of 237 triangles, and this 237 triangle group generating this tiling by 237 triangles, triangles of angles pi by 2, pi by 3, and pi by 7. So if you have a way of identifying these to get a surface below, and these identifications that by translations that preserves this tiling, then this tiling would also descend to the surface. Okay, so that's the way that you can construct. So one of these, this is a kind of a famous example actually. So this is a genus 3 surface that can be built. So I've taken now this fundamental domain, this polygon, composed of all these 237 tiles actually, right? So this you can see this in a layer below, but you can group them so that these are equilateral triangles. Okay, and there are exactly 7 equilateral triangles around this vertex and so on. And now when you identify them according to these labels, right? So for example, this side E maps to E and so on. You get a genus 3 surface with the same property that each vertex has exactly 7 equilateral triangles around. Okay, so this genus 3 surface has a 3-7 tiling. Okay, and so I mean, roughly speaking, so we are kind of choosing these identifications, these translations to be automorphisms of the tiling. So it preserves the tiling. Okay, and so when you pass through the quotient, you actually get a tiling of you also get the tiling descends to the quotient. Okay, so that's what's happening. And this is a famous example because it's called the Klein's quartic. So Klein, in fact, in the 1800s, 1870s or something, came up with this gluing, this particular gluing of this 237 thing, and so he realized you get a genus 3 surface which is very symmetric. Okay, and I'll come back to that point later. And it turns out that this can also be described as in terms of solutions of this equation. Okay, so you have to view these as complex number solutions in CP2. Okay, so you have to projectivize. This is what is called an algebraic curve, right? So this particular hyperbolic surface that you built is actually also described as an algebraic curve with this equation. Okay, so it's called the Klein's quartic, and you can have many more examples of that. So all we really need is to quotient by a discrete group, quotient hyperbolic plane by a discrete group that preserves the tiling, right? So let me just tell you, in general, a Fuchsian group is a discrete subgroup of the isometry group of H2. That's what it's just a name, and such a group acts nicely on H2. Properly discontinuously means sort of it's nice enough. So the quotient is for example, a Hausdorff space. It's nice enough topologically, and it's said to be a co-compact Fuchsian group if the quotient is also compact. Okay, so you get a compact surface, and one example of such groups are exactly these triangle groups that you meant, as we saw, right? So you take a reflections around sides of a PQR triangle, and those generate discrete groups, as we saw, and it's also co-compact because what's the fundamental domain? What's the sort of the basic thing everything comes down to? Well, one triangle, really, right? So that which is compact. Okay, so that's which is compact. It's right. So it fits this this description. It's not quite a surface though, right? It's kind of maybe you can think of it as a triangle with some pointy corners, right? But it's a compact object, right? So that's co-compact triangle group. But it turns out that once you have a co-compact Fuchsian group, you always also have some subgroup where the quotient is an actual surface, one of these, closed oriented surfaces that in the list. Okay, then this is kind of follows from what is called Selberg's lemma, which is more general than this. This is in fact, it's for any finitely generated matrix group, but right. So, but let me just mention it for the Fuchsian group. So, if we have a Fuchsian group, finitely generated Fuchsian group, it has a subgroup of finite index that is torsion free, and torsion free means it is no finite order elements, and these finite order elements, by the way, are the ones which have fixed points in the interior. So you don't want things like that. And if you don't have things like that, so if it's torsion free and it acts properly discontinuously, then you actually get a surface. And since we already, okay, so in this particular case, if you also have co-compact, then you'll get a compact surface. Okay, so Selberg's lemma tells you that if you apply it to this triangle group setting, for example, that tells you that there's a 3D tiling on any compact surface, right? Because not any on some compact surface. Okay, so and I'll come to any a little bit later. Okay, so because you can pass through some finite index subgroup of that triangle group where the quotient is a surface. Okay, and then the tiling descends. Okay, but you can ask, okay, which surfaces can this happen in? Okay, so and this was answered. So this basic. Okay, so here's another fact, by the way. This is called the Euler characteristic of a surface. So you might already have come across this, right? So it's just like V minus E plus F was 2 on a sphere, and in general, on one of these surfaces, it is 2 minus 2G, where G is the genus. And here's a result from quite a while ago. Which is that if you have a PQ tiling on a genus G surface, if and only if the Euler characteristic constraints are met. Okay, so in other words, right. So if V, E, and F are the sort of numbers of vertices, if there are potential integers that satisfy this basic Euler characteristic conditions, then there actually exists a tiling. Okay, so this was the result, and I mean, you can figure out that you can come up with sort of P's and Q's that wouldn't and G's so that there is no tiling. There can't be V, E, and F. So this is one kind of exercise you can perhaps work out, but essentially it's saying that the only obstruction is this very naive Euler characteristic count. Okay, so there are plenty of these kind of PQ tilings. Okay, so and essentially, so in some sense, they arise from subgroups of some appropriate triangle groups in some sense. Okay, so okay, but you can ask for enumeration. So you can ask, okay, so how many are there, for instance, right? So, for example, there are, it turns out this is Basudev Datta, who was my colleague until he retired a couple of years ago. So, so they figured out how many of 3-7 tilings are there on a genus 2 surface, for instance, right? So you can figure out from here, you can kind of figure out how many vertices, edges, and faces there could be, and for each of these there are some such tilings, but then you have to figure out maybe there's combinatorially there are different ways of fitting them together, right? So anyway, so there are they figured out did that combinatorics, but in general, I mean, people haven't really worked out what these numbers, how many counts are in general. So that's unsolved. But you can, okay, so these ones are the theorem that of Edmonds, Ewing, and Kulkarni are not necessarily regular. Okay, I'm forgetting here the last condition of regularity. If you remember that I wanted every vertex to kind of look the same, so this automorphism group is kind of really transitive in some sense, right? And so there's lots of symmetries, and so you can ask, okay, so no, I don't want just same number of polygons around each vertex, and all of these polygons the same. I want them also to look the same at every vertex. And you can ask, okay, so here's my definition of regular tiling, that it has to be, an automorphism group must be transitive on pairs of vertex and edges, right? So every vertex and edge has to go to every other vertex and edge. That edge is incident to the vertex, right? And so you can ask for something like this. And in this context, there's this theorem of Hurwitz, which says that if you look at automorphisms of a tiling, let's say, on a genus G surface, this automorphism group has to have order at most this one. So this is the 84G minus 1 theorem. Some of you might have heard about it at some point. Okay, so right. So maybe I should have. I wanted to mention. Right. So in other words, yeah, we want automorphism group to be large for these regular tilings, right? And so Hurwitz's theorem says this is the largest you can get on a genus G surface. Okay, and the idea of the proof of Hurwitz's theorem is this, that if you have this symmetry group acting on the genus G surface, you take a quotient of the genus C surface by that symmetry group, and that quotient map is what is called a branched covering. Okay, so this is a surface. This quotient thing is not quite a surface always, but it's some, it could be, for example, one of these triangles, and in the triangle group, the triangle. But these are sometimes what are called orbifolds, hyperbolic orbifolds, and so the quotient would be a branched covering of degree d, and you want d to be as large as possible, right? So you want to understand how large can d get. So to understand how large d get, you must understand how small this quotient can be. By the way, something that I sort of forgot to mention, that this you can, instead of in this hyperbolic metric, of course, this Riemannian metric, you can measure distances and all. You can also talk of area. All right, so the area of one of these polygons, let's say these triangles in a hyperbolic plane of, let's say, of angles maybe alpha, beta, gamma. So the area of this triangle is pi minus alpha minus beta minus gamma, right? So it turns out this is positive, by the way, right? Because in a hyperbolic plane. So this is an area of a genus G surface. The area of a genus G surface is always 4 pi G minus 1. Okay, so this is also kind of a fact. So of course here, sort of hyperbolic surfaces, you're now in the realm of hyperbolic geometry, which is genus greater than 1. Okay, so if you have a, so if you want to kind of make degree d large, you want this to be very small, because x would be tiled by this quotient thing, right? So this quotient, you can think of this as like one of these fundamental domains of the symmetry group acting on x itself, right? So you're tiling x by these, and so how many you're trying to understand how many tiles can there be, right? And it turns out that the smallest hyperbolic orbifold is in fact this 237 triangle group that we mentioned here. Okay, so this is area pi by 21. So if you want to find, so now let's say you want sort of integers p and q and r, so that this area is smallest, and of course you want 1 by p plus 1 by q plus 1 by r to be, okay, maybe I should say it's the smallest but positive, right? So this is so you can figure out that this is achieved when p, q, and r are 2, 3, and 7. Okay, and the area is pi by 21. If you plug 2, 3, 7 here, you'll get pi by 21. Okay, so and once you have that, then this you get this degree d is less, this is the smallest possible area, so it's less than area of this, which is this 4 pi g minus 1 divided by pi by 21, which gives you 84. Okay, so anyway, so this is how this comes about. So it turns out that some of these tilings I told you are in fact regular in this sense. Okay, so one of these is this 3-7 tiling of the Klein quartic. The automorphism group is 168, which is 84 times 3 minus 1. Okay, so this was a genus 3 example. So right, so this is in fact a regular tiling, and there are some other examples where it's not quite the maximum. It's not, so it's also very symmetric in the symmetric enough in the sense that every vertex edge pair goes to every vertex pair. This is another example. This is 3-8 tiling on a genus 2 surface. So here, so you take this octagon, the larger one, and you identify sides by pairing opposite sides by hyperbolic translations. And it turns out that if you do this, you get a genus 2 surface. And this tiling that you have by triangles, it descends to give you a 3-8 tiling. Okay, and it's very symmetric, because here you can think about, for example, rotations, right? So rotations that of this hyperbolic octagon, and you can prove that descends to an automorphism of the surface also. Okay, and so the gluing is such that it descends to something like that. So anyway, so this is another regular tiling, and there's also another class of examples coming from Fermat curves. So for example, a Fermat quartic with x to the power 4 plus y to the power z to the power 4. This gives you some 8 to the 3 tiling. Anyway, so there are some examples, and there were some people who did computer calculations that involving finite index subgroups of triangle groups to get kind of a list. So here's the kind of the title of that paper. This was a while ago though, 2001. So I'm sure that people have improved upon it. I mean, the main person I think is this Condor. He did a lot of work, it seems. So I wasn't quite aware of it, but I just this question of symmetry occurred to me while kind of preparing a similar talk, and I was led to kind of figure out, okay, what is known. Okay, and it seems that people have make lists of these regular in this sense, right? So symmetric enough maps, and they made lists using computer calculations, and this is one example of a table from his paper which lists. These are the ones for genus 2. Okay, so the 3-8 one which I mentioned with octagon, and there are a few others. So it also includes something like 8-8, which is basically, if you just take an octagon, right, and then glue the sides like the way that I showed you, or even opposite sides. I mean, essentially you just have one face, right? So you have one face, but you can think of, if you're gluing it up, every vertex you have, sort of copies of that one face around it. Okay, so in some sense you're counting the same face, 8 times. So I think that's what gives rise to this 8-8 example here. Okay, and they figured out what these symmetry groups also are. Okay, so sort of this is a kind of something that people have done. But I don't know whether there's how much they have now and so on. Maybe it's something that. Okay, so kind of run out of time, but if I can carry on, I can do a little bit more about what are called semi-regular tilings. Okay, so semi-regular means I allow different polygons now, different sizes, regular polygons still. Okay, I'm still looking at regular polygons, but different sizes. So, but I want the property that at every vertex I have the same tuple of integers which counts the counts the sizes of the polygons. So there are d polygons and of sizes k1, k2 up to kd around it. Okay, and I'll give some examples quickly. So if you have this, so now I'm kind of discarding that symmetry assumption. Okay, so which is also actually, yeah, I mean, I don't know what will happen if you impose that as well. Okay, but like for example, making it vertex transitive and so on. But here it's just the condition that all polygons are regular and there are same number of tiles around each vertex, and they have sizes appearing the same order. Okay, either count clockwise or anti-clockwise, I don't care. Okay, so yeah, so here's a quick quiz. So which one of these is semi-regular in this sense? So right, so each of these is so you have hexagons, squares, and triangles, right? But now if you notice here, right, so here for example you have a vertex where you have two squares adjacent to each other if you go around it, right? So you have a triangle, square, square, hexagon, right? But this vertex you have a triangle, square, hexagon, square. So that's a different order. Okay, the different permutation, I don't allow that. I want the same cyclic, sort of tuple, all right? So either clockwise or anti-clockwise, one of these two. So this is not semi-regular, but this one is, in fact. Okay, so if you look here, yeah, so you have triangle, square, hexagon, square at each vertex, okay, in that order. Okay, so all right, so this is the notion of semi-regular, and it turns out this has been studied for thousands of years. Again, so people have figured out what are all the semi-regular tilings of the Euclidean plane. Okay, so this is called Archimedean tilings, and these are, okay, so the first three are counted also because these are the regular tilings, but then there are these others. And you might, worry that these two are the same, but they actually mirror images of each other. If you count a reflection as a symmetry, right, then they are the same. Okay, so there are actually 11 such Archimedean tilings. Okay, so and right, so again, I mean, so you can figure out. I mean, it's not too hard to figure out why there are exactly 11. You can list, okay, so these are the possible ways you can fit regular polygons around to get 2 pi, right? So you can start with that, right? At least locally you have to have angles adding up to 2 pi. This is called the angle sum. Okay, so if these are the sizes of the polygons, then if you look at the angle sum, this must happen, right? So for the tuple, these must add up to 2. This is in a Euclidean plane, right? And these are the possible such local configurations, right? And one of the examples, so the largest size that occurs in a local configuration is 42. Okay, so 3, 7, 42, and this is related to this, 20 pi by 21 that we got there. Okay, so this is, but not all of them extend to Euclidean tilings. Okay, so tilings, the Archimedean tilings of the Euclidean plane, semi-regular tilings. So only 11 of these extend to semi-regular tilings. Okay, so that's something again one can work out. Okay, why you can rule out some of them. This is one example of a tiling. Maybe there are others here around in this campus as well. Here's another. They're all quite very nice and symmetric. Again, sort of they have they're all always doubly periodic and so on. So they descend to a torus, and we'll come to that soon. Okay, so these are the Archimedean tilings. Now, okay, so you can ask the same question of the hyperbolic plane, right? So here's an example of 3, 3, 4, 3, 5. That's the tuple. So now the angle sum must be, the way I wrote it has to be bigger than 2, I think, because so now these angles are smaller in hyperbolic plane, right? So So if you just look at the Euclidean analogs, they have to be bigger than 2. Okay, so sort of this angle sum has to be bigger than 2. And so given a cyclic tuple, so the basic questions are as follows. So given a cyclic tuple of integers, so that it satisfies that angle sum property, so that there can be a local configuration of hyperbolic regular polygons, right, adding up to 2 pi. Yes?
In the hyperbolic way, we can move around the shapes to make the angles as small as we want.
Yeah, that's right.
How can we directly conclude that the angle sum, as in the ki's, the ki minus?
Yeah, so the ki's are the Euclidean versions, right? So the ki minus 2's by ki are the angles of the corresponding Euclidean polygon. If you have a Euclidean polygon, so you have a hyperbolic picture. Now if you sort of abstract out each of the polygons and make a Euclidean version of it, these would be the angles. And those angles must have to add up to more than 2 pi. Okay, so that's what is meant by angle sum bigger than 2 pi. By angle sum bigger than 2. Okay, so right. So you can ask, okay, angle sum bigger than 2, does there exist a tiling of the hyperbolic plane? Right, basic question. Is it decidable? Is there a finite time algorithm? Is it, you know, for example, if you start, this is the connection with theory of computation that maybe I'll mention again at the end. So if you have a sort of a tiling, one way, okay, so you can start placing tiles, right? So satisfying this local condition that each vertex has these many, right? So you start placing, and you keep going, but you know, you don't know at what stage you might not be able to, you know, place any more, right? So if you just think about that as an algorithm, that may not stop in finite time, right? So if it has no tiling, it might not stop in finite. So question is there an algorithm that to decide if such a tiling is possible? And if there exists a tiling, is it unique? If not, how many are there? That's sort of the basic way that mathematicians would break up some kind of a problem, right? So here, let me tell you, so full answers are not known. So here's some partial answers to the, let's say, first question, existence question. So there exists a K tiling, you know, with this tuple, with this given tuple, if all of these K's are even. Okay, then this was another paper of Edmonds, Ewing, and Kulkarni, 1982, which I'll mention again a little bit later. Okay, so this is the case where all of these are even. When some of them are even and some are odd, you know, there was a paper of mine with Basudev that we wrote a few years ago. So Basudev was working in the tilings of, or he called them maps actually, of on the Euclidean plane, and he was excited about some recent result they had, and he came to my office, which was sort of almost next to each other, I guess on the same floor at least, and he was telling me about it. So then I asked him the natural question. I'm somebody who comes from the world of hyperbolic geometry, and so I asked, the natural question is what happens in the hyperbolic plane, right? So what happens to the same kind of things? He was looking at Archimedean tilings in the Euclidean plane, and that's how we get, you know, got this talking and discussing, and this was a, you know, sort of a this idea of the proof of this. We got this kind of combinatorial condition on the tuple, okay, and maybe right. So I should explain. If I had more time, I would have explained this better. But maybe I'll skip explaining this. But it's a combinatorial condition on these integers appearing in the tuple, right? And we just proved that if you have a combinatorial condition is satisfied, then you can just keep going and building this, you know, this algorithm I talked about, right? Which might not, you know, halt or might halt. We don't know, but we show that it doesn't halt. And it keeps going if that combinatorial condition is satisfied. And so at the end, you know, when you've done this whole thing, we prove that you do get a tiling of the hyperbolic plane. Okay, and so this gives us a few more examples, but it's still not a complete answer, right? It's just a kind of a one-way existence result that, okay, some tuples do exist, these semi-regular tilings do exist. So one such example is this 4545, where you can do it. But you know, this combinatorial condition that turns out is not a necessary one. it's not satisfied by this tuple, and so, but there is a tiling of by this tuple. So we don't quite know what are necessary and sufficient, if there are some combinatorial conditions which are necessary and sufficient. So that's sort of not yet known. Okay, so and we could figure out that it's not unique in general. So I should have mentioned that Archimedean tilings, exactly 11. So if you specify that vertex type, that equivalent of K, it's unique. Okay, there's only one, except of course that, well, it's unique if you allow for reflections, right? So the same thing is not quite true for hyperbolic planes. So both of these are 4, 4, 4, 6 tilings. And if you kind of look at it closer, you can figure out that they're different. I mean, for instance, yeah. So here, if you look at this red hexagon, and you have to go a few more to get to the next one, right, along this side. But there's no such thing here, right? So that all of them are one unit, 1 square apart, or something like that, right? So I mean, this is one example, I guess. But yeah, anyway, so you can, these are not unique in general. All right, so okay, so here itself, in the hyperbolic plane itself, there are, sort of things are not completely known, but let's move on to other surfaces. So on the sphere, these are the analogues of Platonic solids, which are called the Archimedean solids, and maybe you've already come across some of them. When one of them, of course, you have come across, this is the tiling by hexagons and pentagons, right, which is the usual tiling of a football, right? So, right. So anyway, so there are these many Archimedean solids. Well, actually, there are a little bit more. If you don't allow that symmetry condition, right, that every vertex has to look the same, then there are these two. There's a duplicate, which one of them is symmetric, other one is not, and it's called a pseudo-rhombic cuba. Okay, so all these have names. I'm not going to try to pronounce it, and it's called pseudo because turns out it's not symmetric enough. The automorphism group is not transitive on the vertices, so it was missed sometimes over the centuries when people have found out this list many times, right? Well, actually, this is not all. There are also 2 infinite families, the prisms and antiprisms. Okay, so these are also semi-regular tilings. By the way, I'm thinking of these as tilings of the sphere, again by projecting them to the sphere, right? So you can think of them as tilings of the sphere. And okay, so now let's go to the torus. Well, at the torus, as I told you, these Archimedean tilings are all periodic, doubly periodic. So they descend just like before. These regular tilings descended to give you tilings of the torus. So you can do the same here. And this is one such picture, one of the quotient tilings. I think it had this on the title page of the talk, right? So this is one such. Okay, so what happens in higher genus surfaces finally? Okay, so this is that other paper of Edmund Ewing Kulkarni that I told you about. I think the same year or something. But anyway, so they looked at not just, now they're looking at not regular, but these semi-regular tilings, right? With all of them even number of sides. Okay, this is the case that I said is known. And then what they proved that there's just like in the PQ case, in the regular case, that there's a tiling of genus G surface whenever the Euler characteristic condition is satisfied. Okay, so there is also a similar Euler characteristic condition you can get for these semi-regular guys, okay, just by counting edges in 2 ways. And so once it's satisfied, it has to be satisfied if there is a tiling. So then there is, then there is one. And so what's not completely known then for higher genus surfaces, what if some of the sizes are odd? Okay, and for a while, so Arun Maiti was a postdoc in IISc a few years ago, and I was he got interested in. For a while, I didn't know what So I was telling him I don't know whether 355 there's a 3555 tiling on some closed surface. Okay, and he finally came up with one. This is in a paper of his, and so if you take this and you sort of identify labels which are the same, right? 16 and 20 also appears there. 16 and 20. what you get is going to be a genus 2 surface. Okay, this you can check. You can check Euler characteristic and sort of, and it will have so these. If he's drawn abstractly the pentagons and triangles, right? It will have a 3, 5, 5, 5 tiling. So at every vertex, they will have a pentagon, 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 and one triangle. Okay, so I'll take that. So anyway, so I don't know how he got this figure, but I asked him, but he didn't tell me. But I'm curious. So now, what happens when for other tiles? So one question, for example, I don't know. One of you can figure out, perhaps. 4, 4, 4, 5, for example. All right. So this is another thing which satisfies that angle sum condition, and one can ask if there is a k tiling on a closed surface of genus 2, right? Okay, so for this maybe I know the answer already, but I would so but so you can change, you can play around this. So maybe I should just say generally, let's say PPPQ, where P and Q are distinct integers satisfying that Euler's sum condition. Let's make it a little bit more general, so that to get to a question which I can't quite think do I don't know the answer to. So and if you fix the genus as well, then this question it will be a finite computation actually. So maybe it's possible to just write a program to do that, right? So you just take, you can figure out from the Euler characteristic condition how many the squares and pentagons it would require to get to genus 2, and then you just have to check for what are the possible identifications you can do to get a tiling, and that's a finite check in principle, and maybe it will be a large check, but if you are clever enough to write a nice computer program, maybe this can be done quite easily. So if any of you do that, then let me know. I mean, it will be I think maybe it'll give a clue of the next question which I want to end with. Sorry for going over time, but so more generally you can ask, okay, so if there exists a k tiling on the hyperbolic plane, is there one on a closed surface? Okay, so is there one with enough symmetries so that it descends to a compact surface? Okay, so or can you so right, so is there some k for which there is no such tiling on a closed surface, but there's one on a hyperbolic plane? Okay, so is that possible? Okay, so there's a kind of a paper of Arun where he claims that there is such a vertex type which tiles the plane, hyperbolic plane, but not of any closed surface. Okay, so it's right. So right, this is sort of you can call this a weakly aperiodic. It's called a weakly aperiodic tiling of the hyperbolic plane, because although it tiles a hyperbolic plane, there's no compact quotient, right? There's not enough symmetry so that you get a compact surface. Okay, so these are aperiodic tilings of the hyperbolic plane. So he claims that there is some such aperiodic or weakly aperiodic tiling, but I haven't sort of been able to verify this claim. He doesn't give too much of detailed proof, and so anyway, so if it's there on the archive, if somebody wants to kind of verify this, and this looks a bit long also, right? So we would like something which, okay, so is there one of smaller degree? Okay, is there one with 4 polygons around each vertex, for instance, or maybe 4 doesn't work, 3 doesn't work, we know. Okay, so this is all 3 degree 3 tilings, semi-regular tilings. If there's one on the plane, hyperbolic plane, there's also one on some surface. Okay, they're all symmetric enough, but maybe there's one on. So, and if And if it is true that there's always one on a closed surface, so maybe Arun was wrong, and there's one on the closed surface, then the semi-regular tiling would be decidable. So because what you have to check is for every genus, you do a finite check to check whether it tiles that there's a k-tiling of that surface. And if there's a tiling of the plane, one of these would be tiled, and so your program will stop. Okay, so this is the halting problem, thing is satisfied for this one. So so it would be a decidable thing. So if not, so if Arun is right, and this is is an example of something which tiles the plane but not any closed surface. So there are these weakly aperiodic semi-regular ones. Then maybe one can try to, the question would be, is it undecidable? Can one show that it's actually undecidable, whether the tiling problem of hyperbolic plane, semi-regular tiling problem. Okay, anyway, right, so yeah, as I should mention, there's a kind of a fairly recent book on tilings, which covers more than just these regular and semi-regular, regular tilings or semi-regular, very specific cases, but there's some more stuff here, and you might like to look at this. I'll in fact be teaching a course based on this book next semester at IISc. Anyway, thanks again for listening, and sorry for going over time.
You're just looking at one polygon, right? To see that if it tiles the plane, then it tiles some surface. Then is it force that needs to be the fundamental domain of some function group, or is that not necessarily looking at just one polygon?
Right. So yeah, it's not necessary. Maybe there will be a union of those, which would be a fundamental domain, right? So yeah. So it's a So not necessarily that itself would be the fundamental group of. Okay, thank you. Thanks.